Dear students, in the last class, we have studied about the covalent bonding of the Lewis theory. According to the Lewis theory, covalent bond is formed by sharing of unpaired electrons between the two atoms, and we come across the two types of covalent bonding: non-polar covalent bonding and polar covalent bonding. Non-polar covalent bonding exists between the two atoms of the same element. Polar covalent bond exists between the two atoms of different elements. When we consider the molecules having more than two atoms, then the shape of the molecules or the geometry of the molecule plays a vital role. To explain the geometry of the molecules, Lewis theory could not explain. So, in this the way, the new theory emerged, given by Sidgwick and Powell in 1940, to explain the structures of various molecules. This theory is called valence shell electron pair repulsion theory, commonly called VSEPR theory. As I have said, this theory was proposed to explain the shape of covalent molecules. It was first proposed by Sidgwick and Powell in 1940, and it was later improved by Gillespie and Nyholm in 1957. The main features of the VSEPR theory are listed below. Number 1. The shape of a molecule depends upon the number of the electron pairs, that is both bonded and non-bonded, around the central atom. I repeat, the shape of a molecule depends upon the number of electron pairs, that is bonded or non-bonded and non-bonded, around the central atom. The electron pairs around the central atom tend to repel one another since the electron clouds are negatively charged. The electron pairs in space tend to occupy such positions that they are at maximum distance apart and the repulsive interactions are minimum. A multiple bond, here it is treated as if it is a single bond, and the electron pairs which constitute the bond may be regarded as a single pair. The electron pairs involved in the bond formation are known as bond pairs, while those not involved in any bonding are called lone pairs. Nyholm and Gillespie stated that the electron pairs existing as lone pairs cause greater repulsive interactions as compared to bonded electron pairs. They said the repulsive interactions follow the order lone pair repulsion is greater than lone pair repulsion, which is further greater than bond pair repulsion. These repulsive interactions influence the geometry of the covalent molecules. Covalent molecules can have two types of geometries, namely regular geometry and irregular geometry. Covalent molecules having regular geometry results if the central atom is surrounded by all bond pair electrons with similar atoms. Such molecules have perfect symmetry and they have zero dipole moment. Irregular geometry results if the molecule is surrounded by either bond pairs with different atoms like chloroform CHCl3, or both bond pairs and lone pairs of electrons, example water, ammonia, etc. Such molecules do not have perfect symmetry, hence exhibit some dipole moment. Let us take the molecules which have the various shapes and the perfectness in the geometry. The example beryllium fluoride. Here the central atom is beryllium and the 2 fluorine atom is attached to the beryllium through a covalent bond, and they orient in space as away as possible so that the minimum repulsion between the two is minimum. This results linear shape with a bond angle 180 degree. Consider boron trifluoride molecule. In this molecule, boron is the central atom and the 3 fluorine atoms are connected to boron through bond pair electrons. And these 3 fluorine atoms, they orient in space to give trigonal planar geometry with a bond angle 120 degree. Methane molecule is the another where central atom is carbon, which is surrounded by 4 hydrogen atoms leading to the shape tetrahedral and bond angle 109 degree 28 minutes, and all these bonds are formed by bond pair electrons. Next we take another molecule, Pcl5 molecule, where the phosphorus is the central atom and 5 chlorine atoms are surrounding the phosphorus, leading to the shape trigonal bipyramid with 2 bond angles 120 degree in one plane and 90 degree above and below the planes. And lastly, we take the another example, sulfur hexafluoride molecule, where the sulfur atom is the central atom and 6 fluorine atoms are surrounded by the sulfur atom. This leads to the octahedral geometry with the bond angle 90 degree. In all these molecules, the bond pair electrons are involved and these molecules have perfect shape. This leads to the zero dipole moment in these molecules. Let us take the other 2 molecules like ammonia and water. In ammonia, nitrogen is the central atom which is bonded by 3 hydrogen atoms, and also it contains a lone pair of electron. This lone pair of electron is also to be considered as a bond. Therefore, we come across around the nitrogen 4 bonding electrons. As a result, it produces tetrahedral geometry because of the lone pair bond pair repulsion, which is greater than bond pair repulsion. So the bond angle H and H reduces from 109 degree 28 minutes to 107 degree. Therefore, it exhibits distorted tetrahedral geometry, which leads to the trigonal pyramid geometry. It is irregular geometry, hence the molecule has dipole moment. Coming to the another molecule, that is water molecule, which contains the 2 hydrogen atoms bonded to the oxygen, and also on the oxygen 2 lone pairs of electrons are there. Therefore, we have to consider the 4 bonds. Therefore, this molecule should have tetrahedral geometry. Because of the 2 lone pairs of electrons, it exhibits lone pair repulsion, lone pair bond pair repulsion, as well as bond pair repulsion. Because of this high repulsive nature, the bond angle reduces from 109 degree 28 minutes to 104.5 degree. Hence, water is a bent molecule. Its geometry is more distorted than ammonia molecule. Hence, it is having greater dipole moment than ammonia molecule. So, this is about the explanation based on the VSEPR theory for perfect molecules and irregular molecules having one or more lone pairs of electrons. Now coming to the limitations of Lewis concept. According to Lewis, hydrogen and fluorine molecules are formed by sharing of an electron pair between the two atoms of the same element. As a result, they should have some bond length and bond enthalpy. Experimental results show that bond length in hydrogen is 0.74 angstrom and fluorine is 1.44 angstrom, and bond enthalpy is in hydrogen 435.8 kilojoules per mole and in fluorine it is 150.6 kilojoules per mole. Lewis could not explain this. Moreover, the VSEPR theory is applicable only to the limited number of molecules. To overcome these limitations, the new theory called valence bond theory was given by Hitler and London in the year 1927 and was later on modified by Pauling and co-workers. That's how the VSEPR theory also failed to explain the many molecules. Therefore, the new theory emerged called the valence bond theory. Let us study this theory in the later class. This slide shows about the valence shell electron pair repulsion theory given by Gillespie and Nyholm, and it says it is the space model that is obtained after joining the points represented bonded atoms. That means lone pair are not considered in the shape of the molecule. In order to represent the shape of the molecule, at least 3 atom and 2 bonded pair are required. This slide shows the main postulates of valence VSEPR theory. That is, the shape of a molecule depends upon the number of valence shell electron pairs around the central atom. Pairs of electrons in the valence shell repel one another since their electron clouds are negatively charged. These pairs of electrons tend to occupy such positions in space that minimum repulsion and that thus maximum distance between them. This slide shows some of the basic assumptions what we have discussed earlier. So these basic assumptions are given here. So this slide also gives some of the points of VSEPR theory. This slide shows the structure of the methane molecule and how VSEPR theory explains the structure. So in case of a methane, we have the 4 covalent bonds, and these covalent bonds orient in space to give a bond angle 109 degree 28 minutes. And here all these are as apart as possible, having minimum repulsion between the 2 bonding atoms. This slide shows the various geometries of the molecules when they are attached with the central atom. Here it shows some linear geometry, triangular geometry, tetrahedral geometry, trigonal bipyramidal geometry, octahedral geometry, and even a bent molecular geometries. Yes, this is a slide which shows what we have already discussed. So, if the atom contains one central atom and two attached like beryllium fluoride, it is having linear geometry. So, if it is having the four atoms in a molecule, one central atom and three are surrounded to each other, then it gives the trigonal planar geometry if it is having lone pairs, no lone pairs of electrons. But if it is having one lone pair of electron, it leads to the bent molecule. So the example for trigonal planar is boron trifluoride and bent molecule is water molecule. If the molecule is having 5 atoms, where one is the central atom and 4 are the surrounding atoms, this leads to the tetrahedral geometry where no lone pairs of electrons are there. If the atom is having one lone pair of electron, it gives trigonal bipyramidal geometry with a distortion. And also if it is having two lone pairs of electrons, so it leads to the bent molecule. So this is a water, and previous one is what you can say if the atom contains the 6 molecules where one central atom is surrounded by the 5 atoms. So this gives with no lone pairs of electron a perfect geometry like trigonal bipyramid. If it is having one unpaired lone pair of electron, it leads to the sawhorse shape. If it is having two lone pairs of electron, it leads to the T-shaped, and if it gives 3 lone pairs of electron, it gives linear shape. So like this, even the molecule having 7 electrons where one is the central atom and 6 are surrounded by it, this gives octahedral geometry if no lone pairs of electrons are there. If one lone pair of electron is there, gives square pyramidal geometry. If two lone pairs of electrons are there, gives square planar geometry. If three lone pairs of electrons are present, gives T-shaped. And if 4 lone pairs of electrons are there, it gives linear shape. And for all these shapes, the various examples are given. Now, for the first one, one lone pair of electron is there, then it is sulfur dioxide is an example. 2 lone pairs of electrons are there, sulfur trioxide, and various other ions are also given. Students, go through the shapes and the molecules. Coming to the limitations of VSEPR theory, even though the VSEPR model is useful in predicting the shape of molecules, it does not differentiate between single, double, and triple bonds and does not account for bond strength. Because of this, the new theory emerged, that is valence bond theory. Here also we have the other limitations of the VSEPR theory. Students, go through these things and try to understand about the VSEPR theory. In the next class, let us study about the bond parameters. Thank you.